extensive program of research and development in the field of disc flight, which was started in 1952, is being conducted by Avro Aircraft Limited at Malton, Ontario. Early studies on behalf of the United States Air Force proved the feasibility of a circular planform vertical takeoff aircraft utilizing a system of peripheral jets for propulsion, stabilization, and control. The current phase of the program entails the design and construction of the Avrocar, an 18-foot diameter test vehicle for the United States Army. The Avrocar will take off vertically and carry a useful load of over 1 ton for 125 miles. It is intended primarily for operation within 400 feet of the ground over terrain of not more than 10,000 feet altitude at level flight speeds up to 225 knots. When the basic design criteria for the vehicle were established, construction of a full-scale wooden mock-up was started. Radially disposed ribs with covering skin form the primary structure. Unlike the actual vehicle, which is manufactured in 3 segments, the mock-up was built in 2 halves. A covered superstructure of beams and partitions form compartments for the crew, power plant, equipment, and cargo. The vehicle is powered by 3 Continental J69 engines driving a turborotor located in a central air inlet. The turborotor expels air through ducts formed by the ribs and skins to a nozzle at the wing periphery for propulsion and control. A separate fuel tank is installed for each engine. Exhaust gases from the engines, which act as gas generators, are directed through tusk-shaped ducts onto the turbine section in the turborotor. As detailed design information became available, the installation of systems and equipment progressed. The completed mock-up provided a dimensionally accurate and fully representative model for evaluation prior to construction of the first Avrocar. During manufacture of the first vehicle, the mock-up continued to provide an invaluable check on the arrangement, location, and clearances for various installations. A 1/20th scale model designed and manufactured for use in the Avro ejector wind tunnel provided preliminary data on the aerodynamic characteristics of the Avrocar, both in hovering and in forward flight. To provide more detailed aerodynamic data, a 1/5 scale model of the Avrocar was designed and constructed for testing in the Massey Memorial Wind Tunnel at Wright Air Development Center. Before being dispatched to WADC for installation in the tunnel, the model and its supporting structure, together with integral force balance, were assembled. Tests were carried out to check the functional behavior of the model and the balance. Wind tunnel tests, including flow visualization tests, were performed to determine aerodynamic characteristics and pressure distribution during takeoff, hovering, transition, and forward flight. To investigate the unique system of propulsion and control to be used in the Avrocar, a full-scale 20-degree segment of the peripheral nozzle and outer portion of the wing was constructed. tests were performed at the Coandă Engines test establishment at Nobel. Here, airflows and pressures could be provided to the segment to match those supplied by the turborotor in the actual vehicle. Two spoiler rings in the throat of the peripheral nozzle deflect the jet flow for pitch and roll control. Instrumentation was installed to supply data to automatic recorders and manometer boards in the control room. Vertical takeoff and hovering are achieved by downward deflection of the peripheral jet, which in the proximity of the ground produces appreciable thrust augmentation. Transition from hovering to forward flight is achieved by rearward deflection of the jet. This hovering model was built to investigate the system of stabilization used in the Avrocar. An electrically driven gyro in the center of the model simulates the turborotor and operates gates controlling the emission of air at each tip of the cruciform. Because the center of gravity of the Avrocar is located approximately in the center of the circular planform, stabilization in pitch and roll is required. On the vehicle, the gyroscopic characteristic of the turborotor is used to sense the rate of imbalance in pitch and roll and introduce corrective bias into the flight control system. Later in the program, the 1/20th scale model was modified to provide vertical damping data. This information, together with results from previous tests, was used in conjunction with a simulation study being performed on an electronic analog computer. The analog computer was operated as a flight simulator with representative controls and instrumentation. Response of the airplane to disturbances of varying magnitudes and frequencies, together with coupling characteristics between the turborotor, pilot, and spoilers, and the ensuing effect on handling was investigated. From this, the most satisfactory control system parameters were determined. With the release of drawings of the main structural components, planning and tooling for manufacture of the test vehicle began. The circular planform resulted in an economical tooling program requiring only 10 subassembly jigs and permitting the use of many identical parts. One final assembly jig is used for assembly of the main structural components. Manufacture of the 1,700 different detail parts required for assembly of the major structural components of the vehicle commenced in a security-guarded area where the vehicle was to be built. The basic structure of the Avrocar comprises a center base around which 3 identical wing segments are assembled to form the circular planform. The wing segments are separately fabricated from radial ribs and upper and lower skins. Ducts form between the ribs, provide for the passage of air from the centrally located turborotor to the peripheral nozzle. Together with the center base and 3 additional ribs, the wing segments are married up in a final assembly jig. Engine air inlet ducts, each centrally divided by one of the 3 additional ribs, are formed between the wing segments on final assembly. The outboard end of each of these ribs is reinforced to carry a landing gear leg. As assembly of the primary structure of the first vehicle neared completion, manufacture of detailed parts and major structural components for a second vehicle advanced rapidly. After assembly of the primary structure and the installation of the tricycle landing gear, the vehicle is removed from the final assembly jig. Three transverse beams enclose the turborotor, engines, and fuel tanks within a central triangular compartment. Each engine is installed in a separate bay, and fuel is supplied by three independent fuel systems. Crew and cargo compartments are located outboard of the transverse beams. The turborotor, which is a turbine compressor combination, was developed by Coandă Engines Limited. To achieve a lightweight unit, hollow brazed steel compressor blades are used. In this pilot program, one blade was processed to prove the suitability of the copper brazing employed in manufacture. The two compressor blade segments, a root fitting and a tip fitting, are installed in a jig. Flux is then applied prior to installation in a bell for brazing. The compound shaft on which the turborotor is mounted incorporates a bearing between the inner and outer components, which permits the turborotor to topple fractionally. This motion is transmitted to the spoiler rings in the peripheral nozzle. Radiating from the hub of the turborotor, the 31 compressor blades terminate in fittings to which 31 turbine segments are attached. Each turbine segment incorporates 4 blades. A simulated inner wing with integral anti-swirl vanes was manufactured for the purpose of testing the turborotor. The turbine nozzle ring and turborotor casing were introduced to simulate as closely as possible the conditions under which the turborotor would operate in the vehicle. The completed turborotor was then installed. Finally, it was checked in readiness for the extensive ground test program. The entire assembly was mounted in the turborotor test rig, and the tusk-shaped exhaust ducts used in the vehicle were fitted. To simulate the power provided by the 3 Continental engines, part of the output from one Coandă turbojet was ducted to the test rig.
6.4. Wing main oil 17 to 0. Number 3, 12.2, 11.3, 12.3. Lateral, 5 mils. Vertical, 1.5.
150 hours of testing were accomplished satisfactorily on the first turborotor. Subsequently, a second turborotor, which had been proof tested for 8½ hours, was installed in the vehicle. The turborotor casing with turbine nozzle ring was then positioned. The third engine and its associated exhaust duct was installed. Attachment of the turborotor air inlet fairing followed. During construction, numerous tests were carried out on the various airplane systems. Typical of these were control system checks. Installation of the inner wingtip permitted mechanical checking of the transition control rings. The rings are used to direct air during hovering and transitional flight. After attachment of the outer wingtip, a final check is made of operating clearances. Similar tests were conducted on the spoiler rings and yaw control vanes in the throat of the peripheral nozzle. Fitting of canopies and hatches brought manufacture of the first Avrocar to completion. The vehicle was weighed, and estimated values of weight and balance were confirmed. After weighing, the Avrocar was moved from manufacturing into the test area. This marked the end of the first part of the contract, some 2 months ahead of schedule. In the test area, equipment will be installed in the vehicle in preparation for the ground test program. Successful completion of ground tests will enable flight testing to commence and provide information required for development of the Avrocar. Produced by Avro Aircraft Limited at Malton, Ontario, the Avrocar symbolizes the culmination of the second stage of an extensive program of research in the field of disc flight. 2 identical vehicles were built for the purpose of conducting static tests, full-scale wind tunnel tests, and flight tests. Wind tunnel tests were performed at Ames Research Center, California, and static and flight testing was carried out at the Avro Test Facility near Toronto, Canada. For static testing, a rig was constructed to support the vehicle at varying heights above the ground. Strain gauge dynamometers at the 3 attachment points permitted lift and side forces to be measured throughout the program. Instrumentation, control, and fire extinguishing lines were installed from the vehicle to the adjacent control room. A remote fuel supply minimized the fire hazard. The first vehicle, completed in May 1959, was installed in the rig for an extensive series of static tests before being dispatched to Ames Research Center for wind tunnel testing. Initially, the vehicle was operated from the control room, where remote instrumentation recorded engine and turborotor performance, duct pressures and temperatures, and spoiler control positions, permitting comparison between theoretical and actual results. Static testing extended over a period of 5 months, during which time 32 hours of testing were performed without failure of any major component. Minor modifications proved desirable by analysis of early test data were introduced both into the test vehicle and into the second vehicle now nearing completion. Typical of these was the modification of the exhaust boxes to improve temperature distribution and introduction of a cascade beneath the turborotor to improve duct flow. The engine inlets were also modified to breathe from the upper skin in order to reduce high inlet temperatures experienced in early tests with the engines breathing from the internal ducts, and further tests were then performed. Introduction of these modifications enabled operation of all engines at full power. Tufting on the underside of the vehicle was used to provide visualization of the focus jet. Later in the program, the remote controls were replaced by the actual cockpit controls. It was now possible for the first time for the pilot to check performance and control characteristics with the vehicle in the flight configuration. Data obtained from oscillograph traces which recorded moment, lift, and center of pressure with variation of control position during static tests was punched onto IBM cards and fed into the IBM 650 computer. The output cards from the computer were then plotted to provide control characteristic curves. Using this data, control system problems were accurately simulated on the analog computer. The aircraft cockpit and pneumatic control system were reproduced using a compressed air supply in place of engine bleed air. The effect of control system modifications was also investigated before changes were made to the test vehicle. As testing of the first vehicle continued, manufacture of the second Avrocar was completed. Preparation was made for the initial engine run, and for this test, the vehicle was secured by cables attached to each landing gear leg. This tie-down arrangement permitted checking of the engines at power settings in excess of the unstick setting, and also provided an opportunity for instrumentation and controls to be checked prior to tethered flight. Subsequently, the test was repeated with the vehicle raised on jacks in order to determine the effect of height on engine inlet temperatures, which were believed to increase due to recirculation of exhaust air. Tethered flying commenced with the vehicle restrained by 3 cables attached to the hoisting lugs and to anchor points in the concrete apron. During testing, the temperatures of critical items of equipment were recorded in the control room. Intercommunication between the pilot and the control room permitted monitoring of the tests by the flight test engineers. An alternative system of tethering in which the vehicle was restrained by weight rather than by rigid anchor points was then employed. Some difficulty was still experienced in controlling the vehicle due partly to the influence of the tethers and partly to loss of lift with control application, which had also been experienced during static tests on the first vehicle. The control system was modified and the vehicle installed in the test rig with the upper nozzle closed except for 4 20-degree segments at the cardinal points. Tests were conducted with different central jet arrangements and various spoiler configurations. Meanwhile, after 32 hours of static testing, the first vehicle was being inspected and overhauled in preparation for the wind tunnel test program. Instrumentation specified for the program was also installed. Finally, the vehicle was crated in preparation for shipping from the Avro plant at Malton to Ames Research Center in California. Rig testing of the second vehicle continued, and the addition of extension links permitted the vehicle to be tested at different heights above the ground, and also allowed application of pitch during testing. These tests indicated some improvement in control characteristics, and the vehicle was returned to the tethers where static test results were confirmed, although the tethering cables continued to introduce random inputs, making accurate assessment of stability and control difficult. Sufficient data had, however, been recorded and analyzed to indicate that operation without the tethers was now possible. On November 12, the Avrocar made its first free flight. In free flight, the vehicle showed a marked reduction of the oscillatory tendency experienced in the tethers. Control sense was correct, although more control power and less lag was obviously required. The number of control sectors was increased from 4 to 6, and after a further period of static testing, the vehicle was prepared for free flight in this configuration. With the increased control power provided by the 6-point system, the behavior of the vehicle was much improved. Stability within the ground cushion was better than before, and the gyro-stabilizing effect of the turborotor was now apparent. Although several satisfactory flights were made, it was realized that one characteristic of the spoiler control system in particular was compromising the performance of the aircraft to a greater extent than had been anticipated. Application of control reduced lift on one side of the aircraft with no corresponding increase on the opposite side. The ideal system would be one which would move the focal point of the jet without loss of lift. A system providing these characteristics had been designed and was being tested on the 1/20th scale model. A focusing control ring around the lower periphery of the vehicle replaced the spoiler control and deflected the jet to provide both control and forward thrust. Static test using steam provided flow visualization of focusing ring control operation both in free air and near the ground. Static and forward flight force tests were performed in the Avro wind tunnel, and flow visualization tests were also performed in the forward flight configuration. After successful completion of model tests, the system was installed in both vehicles. A further period of development in the static rig was required to check the characteristics of the new control system before flying continued. Most of the effort during this period was devoted to achieving a system in which the power required to operate the focusing control ring was compatible with the pneumatic power available from pilot and gyro stabilizer inputs. Tethered and free flights which followed were directed toward increasing the stability of the vehicle in the ground cushion and increasing the stable height of the ground cushion. Development of the new control system resulted in a marked improvement in attitude stability, control sense, and response rate. At a height of 3 feet and at forward speeds up to 20 knots, the vehicle no longer displayed the previous tendency to oscillate after pilot inputs, and short, stable flights with hands off were now possible. The height at which the ground cushion tends to become unstable, now known as the critical height, was found to occur at the point where the simple annular jet formed near the ground changes to the focus jet formed at increased height. Any change of attitude with the aircraft at this critical height causes the jet to become focused on the upgoing edge while remaining unfocused on the downgoing edge with resultant hysteresis. An additional, more powerful central jet was added to improve ground cushion stability. It was found, however, that an increase in ground cushion stability was accompanied by a decrease in control power, and the final configuration represented a compromise between the two requirements. Tests were also performed to establish the stabilizing effect of the gyro stabilizer, and it was determined that signals resulting from small changes of attitude were being lost due to system friction and control ring hinge moment. It was apparent at this point that some form of assist was required to transmit stabilizing signals from the gyro to the control ring, and design of a pneumatic booster was commenced. At Ames Research Center, the first vehicle was now ready for installation in the 40 by 80 foot subsonic tunnel. Here, tests would be performed to determine the transition trajectory from hovering both in the ground cushion and in free air. These tests were all performed using the focusing ring control system, which had resulted in the most successful free flights on the vehicle at the Avro test facility. The variable mount permitted testing to be carried out at heights up to 12 feet. Flight tests on the second vehicle were discontinued to permit introduction of the pneumatic control boost system. This involved the introduction of 6 sensing nozzles at the base of the central control shaft to monitor 6 pneumatic actuators mechanically connected to the control ring. The base of the shaft was now secured by a flexure, and only a small travel was required to transmit gyro-stabilizing signals to the actuators operating the control ring. Functional and frequency response tests were carried out with the pneumatic system pressurized from an external supply. A variable speed mechanical shaker was used to excite the control column, and measurements of control ring motion were made using potentiometers connected to a continuous trace recorder. Subsequently, the tests were repeated with engines operating and the system pressurized by engine bleed air. Tether tests were performed to permit final checking of the power-boosted control system before free flying was resumed. Flights with the pneumatically boosted control system showed a marked improvement over the previous configuration. Stabilizing signals from the gyro were now quite apparent. The pilot reported that the feel of the aircraft was better with the new system, and that precise positioning without excessive effort was now possible. In summary, development of the vehicle resulted in a gradual improvement from the relatively unstable first flight requiring rapid pilot inputs, through various applications of the spoiler control system, which was abandoned due to lift loss with control application, and ultimately to the introduction of the focusing control ring, which resulted in the most significant improvement to date. In the most recent configuration, with the addition of the pneumatic control boost, the vehicle displayed stable flight characteristics at a height of 3 feet and at speeds up to 30 knots. The wind tunnel test data showed, however, that the focusing ring control, though it had been developed for satisfactory hovering, was not good enough for forward flight, and that fairly extensive modifications were required to add an improved forward flight control system. Testing was therefore discontinued until the two vehicles could be modified in readiness for further wind tunnel and flight test programs. Following the introduction of modifications which had been indicated by the results of full-scale tunnel testing of the Avrocar at NASA Ames Research Center, a continuation test program was begun. The objective of this program was to prove the effectiveness of the new control system from hovering through transition in the presence of the ground up to free flight conditions. The program consisted in the main of further wind tunnel tests at Ames Research Center to prove the effects of these modifications, with a short flight test program at Avro to establish that the hovering capability had not deteriorated. A brief terrain test program was later added. The modifications provided for aft deployment of the peripheral jet sheet from the wing tip for transition and forward flight. Both vehicles were modified, one for further static and flight testing at the Avro facility, and the other for tests in the 40 by 80 foot tunnel at Ames Research Center. The changes were confined mostly to the wingtip, which was modified to divert the annular jet aft for increased forward thrust and improved aerodynamic and control characteristics. Transition doors, which extend around the sides and rear of the vehicle, act as flow splitters to divert the flow gradually from the annular hovering nozzle to the new wingtip nozzle for transition to forward flight. With the transition doors in the forward flight position, wingtip cascades at each side of the vehicle direct the jet flow aft. Pitch and roll control in forward flight is provided by the addition of 6 control vanes which operate in conjunction with the existing focusing control ring. On completion of the modification program, the vehicle was installed in the static test rig for functional checking of the new control system and to determine as far as possible that the vehicle performance in the ground cushion had not deteriorated as a result of the modifications. Lift, propulsive thrust, and rolling and pitching moments were measured during the 4-hour static test program. For rig testing, the control system was actuated by an external hydraulic system to be sure of maximum control movement. Tufting was used to provide a visual indication of control vane operation and jet flow. On completion of rig testing, the hovering behavior of the aircraft was checked in the tethers before commencing free flight. It should be understood that the original objective of the flight testing in this program was simply to determine that installation of the modifications had not resulted in deterioration of the vehicle performance achieved during previous tests. Early flights revealed that some deterioration in stability and control had in fact resulted from introduction of the modifications, and a number of flights were required to restore the vehicle performance in this respect. During this 6-hour flight test program, various minor experimental modifications were therefore made to the hovering control system and to the central jet configuration. The forward speed of the Avrocar, with the transition doors closed, was found to equal the speed previously achieved. Operation of the transition doors was attempted, but it was determined that the pneumatic boost available for the control system was not sufficient to overcome the large asymmetric load on the focusing control ring. A more powerful control actuation system is planned for future development. In its current configuration, the Avrocar was operating successfully in the ground cushion at a height of 3 feet and speeds up to 30 knots. Preliminary results from the new series of tests at Ames Research Center were also satisfactory. It was now desirable to extend the Avrocar's operation, and the program was extended to include flights over various types of unprepared terrain and natural obstacles. Initial tests over gravel and small surface irregularities presented no problems. We were now confident of the vehicle's ability to negotiate appreciable obstacles, and a rugged course, partially gravel and partially grass, with a 3-foot deep ditch, was selected for the next flights. Again, the Avrocar covered the course successfully, becoming, as far as we know, the first ground effect machine to negotiate obstacles of this nature. The vehicle had now clearly demonstrated its ability to operate over unprepared terrain, and landing pads were installed in place of the wheels for the following phase of testing, which included operation over soft ground. A number of flights were made over this course, which had a rough, eroded grass surface and a short 1-in-8 gradient. During most of these early tests, ingestion of low-density material presented some difficulty. The fuel control unit filters became blocked with small particles, causing the engines to be starved and resulting in flights of short duration. The problem was caused largely by dead grass and weeds. In an attempt to reduce the ingestion problem, screens were fitted to the engine inlets. No great improvement was achieved as the coarser material tended to block the inlets while fine particles still reached the fuel control filters. Introduction of additional filters resulted in some improvement, and it is anticipated that this handicap will be overcome with little difficulty during further development. In preparation for the final contractual demonstration, a representative course was selected where the vehicle could demonstrate its capability while remaining in view of the observers. The course was laid out to cover concrete, grass, and gravel. Precise directional maneuvers were necessary to avoid surface obstacles. Check flights over this course were performed as the next part of the terrain test program. Erosion due to jet impingement was not found to present a serious problem, and after numerous flights over the same course, only temporary grass browning occurred. In previous flights, the Avrocar had always flown directly over ditches encountered in the course. In order to prove that the ground cushion was not destroyed by sustained flight over depressions along which the jet may tend to travel, it was decided to hover the vehicle over the ditch and then fly out. Before the actual flight demonstration, the Avrocar was flown by a pilot from the United States Air Force Flight Test Center. Familiarization flights were first made over the concrete apron. Additional flights were then made over the demonstration course previously negotiated by Avro's test pilot. Despite unfavorable weather on the day of the flight demonstration, the Avrocar again displayed its ability to operate over terrain which had hitherto been beyond the capability of ground effect machines. In summary, the flight test program at Malton, concluding with this flight demonstration, was carried out concurrently with an extensive 54-hour test program on the second vehicle at Ames Research Center. The tunnel tests showed that if the known thrust losses were to be reclaimed, then the originally estimated performance was realistic. Also, that with the new transition control, transition from the ground cushion to in-flight was feasible. Throughout the entire Avrocar development program, vehicle performance has been compromised due to thrust deficiencies, and it is apparent that if height and speed are to be increased, an increase in thrust is essential. Studies already carried out indicate that a considerable thrust increase could be achieved by reducing turbine tip clearances and by redesign of the ducts, particularly in the region of the final nozzle. With a suitable thrust improvement program, it is believed that a static thrust in the order of the original estimate can be obtained, thus enabling the Avrocar to achieve vertical takeoff and free air transition to forward flight.